In this video, we shall discuss the chemical properties of this thiranes, right? So chemical properties is nothing but the chemical reaction. So chemical reactions of this thiranes. What is thirane? Thirane is nothing but it is three-membered heterocyclic compound containing sulfur as a heteroatom, and it is non-aromatic, right? So it is saturated heterocyclic compound. It is saturated compound. So let us see few of the chemical reaction. Before going in detail with this, let us see few more things of this. Let us compare this thyrane and this epoxide, right? So here both belong, sulfur and oxygen belongs to same family, right? So here oxygen is there, down we get sulfur, right? But the size of sulfur is more bigger, because as we go down the group size increases, and also electronegativity you can see it will be 3.5 and it is 2.5, right? So less electronegative. So we know that electronegativity is nothing but the properties of atom which has ability to hold a negative charge or the lone pair. So if you compare, right, that thing also you should remember. So here sulfur is having two lone pairs and oxygen is also having two lone pairs, right? So if you see, this oxygen can donate lone pair easily to any Lewis acid or H plus or any electrophile like this acyl chloride. This is electrophilic carbon, right? So it can easily donate compared to this thyrane. The reason is, see here oxygen will this thing I have explained in the first class only, but still I have to do here. So it can easily give its lone pair easily, as oxygen is smaller in size, its electron density will be more in a small space, whereas sulfur it's bigger in size, so the electrons will be there here. So size is big, two electrons, so electron density will be less here. So here low electron density is less, whereas here in oxygen electron density will be more. This thing you need to remember, right? So these are the extra points you need to remember. So why I told all these things, right? So because it can easily donate its lone pair compared to this thyranes. So what happens, it will undergo easily electrophilic ring opening reaction. So here we are studying the ring opening reaction, right? Compared to this will also go, no doubt it will also go electrophilic ring opening reaction, but it will be little slow. Rate if you see, it will be slow, whereas its rate will be fast. That thing you need to remember. And also, what about nucleophilic ring opening reaction, right? So both this and this, right? Oxirane and this thyrane both will give nucleophilic ring opening like same kind. The rate will be almost same, right? So these things you need to remember. So first let us we have discussed all these basics. Now let us see this reaction, right? So what is that? Nucleophilic ring opening. I hope you are understanding my handwriting. New opening reactions, right? So here what we will take this thyrane. Here we add nucleophile. It can be ammonia, those nucleophile, right? I will give hydride H minus will be there. If grignard reagent R minus will be there. These nucleophile. Here nitrogen will be. So what happened? Here SN2 reaction will undergo. So we will get SN2 product. And also you need to remember that, see here with red marker I am using. See here this carbon only, here stereochemistry will change. If I write the product, I will take example, then you will get to know. Then simply here the nucleophile will attack like this ring opening occurs, and we will get this product. How this sulfur get H, you should know. And here NH3 was there, it becomes NH2, right? That proton it has exchanged. That thing you should know. I think you know sulfur will be negative charge as soon as it breaks the bond, and this nitrogen will be having NH2H plus charge. So what happens, it will take this proton. So I call it as exchange proton exchange, or we simply call it as fast proton transfer. This it will be very fast, so we call it as H plus transfer. I hope you know these things, right? So let us see a few examples, then you will get to know the stereochemistry, everything. Those are except that thing you will get to know, right? Let me take this, right? This is thyrane. Here see R is above and this hydrogen is below. Here R is above and this hydrogen is below, right? So this is cis kind of compound. To this I am going to add this Li Al. Instead of H4 I am going to add D4, so it can give 4 molecule of D minus ion, right? 4 molecules will be there. So here it is simply nucleophilic addition reaction, so here occurs, so this bond will be broken. And I have told you need to concentrate on this carbon, because the SN2 reaction is occurring to this carbon. Since the SN2 reaction is occurring to this carbon, there should be inversion in configuration. So see, while writing product, how I am going to write, just I will put SH here. This carbon, everything remains same. R is above and H is below. Everything remains same. But here in this carbon, initially it was above R, but now I am going to keep that R below, and I am going to make this hydrogen above, and this nucleophile D came, right? It will be in the plane like this. So this SH and R and this carbon carbon bond all are in single plane, right? And above bond I have represented by wedge bond, right? These things you should know. It is above, it represent below, and single line represent in the plane, right? These things you need to remember. We call it as wedge bond. This is hashed something, it's a hashed bond, and it is simple line. So this represent above, this represent below, and this represent within the plane, within the plane. I hope these things you know, right? So let us see all the examples, right? So same terrain I will take. Here, see here, above I have kept R, below I have kept H. Here also above I have kept R, so below here H. So this is cis thirane, right? To this I will add one more nucleophile, that is ethanol. So here oxygen will be having lone pair. So here stereochemistry of this carbon only change. This stereochemistry won't change. Only here stereochemistry change, right? So I'll get this product. See here, sulfur will be there. Here, see here. Here OET I will write here. Sorry. I have to open the ring, right? So I have to open it. Just I will write here. See here. Right. So here it becomes HS, SH, and here OET. And here H R was above, now it became below, and H was above, below, now it became above. And here everything remains same. R is above and H is below, right? Similarly, you can use one more reagent like RNH2. So it is primary amine, right? So this is primary amine. I hope you can write the product, right? OET instead of OET, you please place NHR there, right? Then you will get the product, right? If what happens if we use polar solvent is there, see here, that thing you can easily understand here. So here sulfur is there, and this is here pH group is there. pH means benzene ring, but one hydrogen will be replaced by this thirane group, right? So this is the phenyl substitution, right, to this thirane. So here water means polar reagent, right? So here what happens, we have two conditions. So what happened, see here, because of this pH group, the bond will cleave here initially, and also because of this polar solvent. Why it will cleave, everything I will explain. So here S gets negative charge and this carbon gets positive charge. Let us look like this, right? So this carbon will be stabilized by this pH group. How it will stabilize, here pH structure you should know. So this is pH group, right? And here this carbon, and here S minus is there, this positive charge. So here from this resonance it will stabilize like this, right? So whenever there is polar solvent is there, we will get product to be this one. See here, further what happens, this will be stabilization structure. I hope you understood, right? So this positive charge can be stable. So this nucleophile, that is water molecule OH, H, it is having lone pair, it can attack here to this carbon, right? So if you see this OH, I'll get here, and S minus will be there, from water it will get proton and it becomes SH, right? Like this ring opening. If simple base, if we have used and it is non-polar solvent, then we used to get product this one. This used to attack this carbon, where it is less hindered because it used to do SN2 reaction. But in polar solvent, it will go through SN1 reaction. How I'll tell that it is a SN1 reaction? Because here carbocation is formed. See here, you can observe. So whenever there is formation of carbocation, it is through SN1 reaction. And also in SN1 reaction, you can show through carbocation intermediate. Otherwise, for shortcut purpose, you can directly write it will attack that carbon which is hindered in SN1. Like that, you can conclude SN1 means it is through carbocation. But for shortcut purpose, you can attack directly nucleophile to hindered carbon. Because whenever carbocation is formed, there should be hindrance, because that will stabilize that carbocation. So hindered group. And also order, tertiary, secondary, primary for SN1. So hindrance should be more, so that it will stabilize it, right? And for SN2, there is no intermediate, just it is through transition state. And also nucleophile will attack from unhindered, right? So order of SN2 you have seen: primary, secondary, tertiary, right? These things you should remember, right? So this is how we will get to the different product, right? Here, if you directly react this in presence of polar solvent, we will get this product pH, and here OH will be there. Sorry, this carbon, right? So let me write like this, right? So it will be like OH, pH, CH2SH, like this product which I showed you, right? So here I am seeing same product like this. So it is through SN1 reaction. If it is like ammonia, SN2 reaction, right? So it will attack here. So I'll get this product, see here, which I am writing with red marker now. Below pH is there, and here I will get this SH, and this carbon ammonia will attack and it will form NH2. Like this product will get. So see here the difference. These are the two different product I will get. Just to compare these two, right? I hope you got it. What all the things I have explained it, right? So next, let us see. I hope this is clear. Now let us see one more ring opening reaction, that is but through electrophilic. So we call it as electrophilic ring opening reaction of this thiranes, right? So let us see that. A nice example let me take. So this is a very good example. Here sulfur is there. To this I am adding electrophile, that is HCl. H plus will be there, Cl minus. So sulfur will be having lone pair. It can easily donate. But if we compare same thing with this epoxide, the reaction of this will be fast with electrophile. It can easily donate fastly. So this will be fast, this will be slow. The reason I have explained, right? Just you remember those things. So what happened? Sulfur donated it, so it got positive charge like this. So now Cl minus is there, so it will attack this carbon and this bond will be broken and it will become like this. Here chlorine and here SH, right? Everything remains same as it is, right? I hope you know. If since it is a symmetrical, no problem. Since it is symmetrical uh, thirane, no problem. If we have unsymmetrical thirane, then what it will happen? Let us see that. So see here R is there, here 2 hydrogen, so it is unsymmetrical thirane. So to this, if I add one electrophile, see here, this is electrophile. How it will react? It will react like this, right? So what I will get? I will get like this compound, and Cl minus will be there. Whether Cl minus will attack here or this carbon, you need to know. If polar solvent is there, then this Cl minus will attack here in polar solvent, like it will do SN1. We can call it as SN1 reaction, or loose SN2 we call it as loose SN2 reaction in presence of polar solvent. In presence of non-polar solvent, then it will attack sterically less hindered and it will go through SN2 reaction, right? So a solvent plays very important role, right? So SN2 means less hindered side attack occurs, and also there should be inversion in configuration. Whenever SN1 reaction happens, there no inversion in configuration. We will get both the product, inverted product and also retention product, because it is through carbocation, which is planar sp2, right? So whenever carbocation is there, it will be in a single plane. So the next coming nucleophile can attack above the plane or it can attack below the plane. So in SN1 reaction, we'll get racemic mixture, we call it is, because we'll get both the product, inverted product as well as retention product. So racemic mixture will get these things, right? So based on solvent, we can write both the product. If polar solvent is there, so I have told it will attack this carbon, right? So I'll get this product C here. Just I'll make Cl here, CH2, S, CO, CS3, and here R. If non-polar solvent is there, then it will attack here SN2, less hindered site, and here I'll get like this Cl and here S, CO, CS3, right? So S, CO, CS3, instead of writing all these things, I have told just simply write SAC. So AC means acetyl group. See here, acetyl AC stand for CS3CO group, right? Simply we shortcutly we call it as AC, right? So SAC, if we write, it is understood that SCO CS3 group is there, like that. Hope you got it, right? Further, let us see one more electrophilic reaction. That is, I'll take this thirane only with R. Here, I'll add anhydride, right? Anhydride. So here it is attacks here, it comes again back, and this is the good living group, it leaves the system, right? So what I'll get this kind of compound. So CO CS3, instead of writing COCH3, I will write OEC, and here I got this thing, O minus and methyl, this thing. So this O minus is there, so sulfur now got positive charge as it has donated lone pair. So it can, since it is sterically hindered, see here, so most of the case times it will attack here only, less hindered site, as it is sterically hindered. It is sterically hindered, so here it is less hindered. So it will attack that carbon only most of the time, right? If we use polar solvent also. These things are the little exception. So what happened, as it attacks here, this bond comes on sulfur and sulfur becomes neutral. So here I'll get O, CO, CS3, and here sulfur, S, AC. That I will write AC instead of writing COCH3. I hope you got it, right? So this is the product. So these are the few electrophilic reactions, right? So next, let us see desulfurization reaction. So the third reaction of this thiranes, that is desulfurization. Desulfurization, right? So what happens is that desulfurization means we remove sulfur group from this thirane, right? How we remove that thing we shall see now. So first let me take one example here, like this. So here R, it is cis thirane. Cis means we can show both are above or both are below, right? It is left to you how you are going to take. And we add these compounds POR thrice and lone pair, so it can donate its lone pair to sulfur, right? So what happened, see here, as soon as it donates, I should not show it by charge. In organic chemistry we never show. Just what we do, just we shift like this, electron density like this, and this bond will be taken, and this we will get directly this product R. Here cis alkene only we will get H here, L, H here, and here we will get this OR, 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 right? Like this we will get. I hope you got it, right? So here this was cis thirane, we got cis alkene only. So it is stereospecific reaction. Stereospecific means stereospecific. Cis remains cis in product. Trans remains trans in product. Right? In reagent cis remains cis. Sorry, cis becomes cis product. Trans becomes trans product. Like that you don't remember. Those reactions are stereospecific. Right? In this organic chemistry, see, just I am with red marker I am showing. We always show these arrows only directly. Like this, it will attack to sulfur. So this bond will be broken, and from this electron density one sulfur phosphor bond will be there. Again one more sulfur phosphor. So we will get this double bond. That thing you need to understand. Otherwise, if I want to show it by charge, I can show it, but we never do this in book. We never get like that, right? So but for understanding purpose, you can show with charge also. See here, which I am showing now. So as soon as it you donate electron density, it gets negative charge sulfur. So what it will do, it will give its electron density to this carbon. Other things you keep as it is, R here, right? So what happens here, carbon gets negative charge, R gets R, and here sulfur gets neutral now, R3, and phosphor, as it has donated lone pair, it gets positive charge. Further what it will do, see here, just it will donate like this bond comes on sulfur. For understanding purpose, it is nice, no problem. So double bond you will get, and here sulfur gets negative charge, phosphor is having positive charge, and OR thrice, right? So positive negative, they will combine to form a neutral and double bond. P double bond is OR. Just you keep OR, right? So like this the reaction you can understand, but I have told how to show that arrow, like that only you need to show, right? In book also you will get like that only, right? I hope you got it. So let us see one more reaction, that is also miscellaneous reaction of this stereospecific reaction. See here, it is also interesting. So here R, this is also cis alkene. Cis you can show both are above or both are below. Now let me show you both are below now, right? So then here hydrogen will be above, you can show that, or it is understood. And sulfur and carbon all are in one plane. So here to this I will add methyl iodide. So sulfur will be having lone pair, so it is simple SN2 reaction. So what happened, I will get this product. See here, methyl came here, other thing remained as it is, R below, and sulfur gets positive charge. Here methyl I can show, or other simple line also represent methyl, right? So iodine, I minus left the system, right? So iodine will be there in the system. So what I minus will attack this carbon, since both are symmetrical carbon, it can attack anyway, but we'll get only one product. So what happened, I'll get R. See here, this R is there, and here iodine attacked, and here R is there, and here sulfur got Me, and it became neutral. So again methyl iodide will be there. So what happened, it will again donate its lone pair, SN2 reaction. I can write like this, sulfur Me, and sulfur gets positive charge, and here R is there, and here iodine is there, one R is there, right? So I minus is there in the system. So what it will do, it will take this iodine, this electron density moves here, this takes the electron density and it goes. So we will get alkene. What kind of alkene? Again we will get cis alkene. So this reaction is stereospecific. Cis thirane will give cis alkene only, and other product byproduct will be dimethyl sulfur, like this. This is the product. I hope you got the mechanism, right? So just you follow with me how I am writing, right? And then you can take the note of it, right? So this is the reaction. So every time I have used, simply I have written R, right? So if R, so R can be anything here. I have written R. So R can be anything like methyl, ethyl, propyl, those things, or tertiary butyl, right? If R is any conjugation bond is there, like pH, if we take, then same, if I just heat it, only these compounds, thirane containing this pH groups, like conjugated groups will be there here. So there will be conjugated bonds like this, right? Pi bonds. So conjugated groups are there. Then what happens, whenever we heat this reaction, simply this kind of reaction it will do. It will take the electron density becomes negative, it becomes positive no initially, so this bond will be broken, again it becomes neutral, and we'll get this pH alkene will get and plus sulfur. So this is desulfurization reaction. I hope you got it. The mechanism is simple like this only, pH and this sulfur. So this electron density moves here, and this electron density, and we'll get this pH, like this only purpose. you can understand like that, right? I hope it is clear. So this is also a desulfurization reaction. It will be given only when there is conjugated pi bonds, right? Then only it will give that reaction. So let us see the last reaction, that is desulfurization reaction. No, no, not desulfurization. It is ring opening and then ring closing. Again ring closing occurs. How it happens, everything we shall see with this example. So it occurs in presence of photochemical condition. So it is also called as photochemical reaction, as it occurs in. So what I will do, I'll take this compound thirane, pH, pH, pH and pH, right? So H nu light is there, that is UV light we are going to use, right? So what happened, you can remember, just they never gave you any mechanism in book, but for understanding purpose just you split like this. So what happened, I'll get this like this: sulfur, pH is there, pH is there, negative charge that will be stabilized by the pH pi electrons, and here carbon gets positive charge and that will be stabilized by the pi electrons of this pH, right? So the properties of this pH groups here, like this it will be. Here it can be positive or negative, both can be stabilized, they can stabilize it by this pi electron. If positive, it will give the electron density. If negative is there, they will take electron density like this and they will stabilize, right? These things you know, right? So no need to discuss them like this. To this, if I add any substance like this, so it will be like 1,3 dipolar species, right? Both dipolar means both pole, positive pole, negative pole, both are there, right? And 1,3 position, right? To this, if I add any substance like this, Cn, 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 then simply reaction like this it will go, and we will get, see, initial ring open it has made, further link closing it will do, and other things remains as it is. Cn, 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 and here everywhere pH, 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 right? So this is how the reaction happened. I hope you got it, right? So electron density it gives to this carbon, further from this carbon it attacks here, right? So we will get this product, right? So last reaction, small reaction, let us see that, and we shall end this thiranes. So here also pH is there, pH is there, pH, and here also reaction is going in presence of formaronitrile light condition. Here desulfurization occurs, right? So what happened, simply like this you can remember, it electron density moves and it takes the electron density, becomes neutral, and we will get alkene only. pH, 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 and one sulfur atom which is neutral, right? Like these are the few reactions of these thiranes. In next class let us see one more compound. Till then, take care.